All right. Thank you for this nice little jingle, and welcome from my side. So welcome to actually the second spring session of the day. I suppose some of you might have been to the Reactive Spring session before. I barely see you, but could you raise your hand if you've seen Reactive Spring with Josh and myself before? Okay, thank you. Inverse check, who has not been to Reactive Spring before? All right, you're in the right place either way, but I will connect to some of the topics from a different perspective, so we are by no means depending on the previous talk. It's more the other way around. This talk was actually originally scheduled before the other talk, but that's a different topic. All right, so for the purposes of today's session, I'm going to take you on a little bit of a tour through the Spring Framework 5.0 release. I will conclude with some things that we are working on for 5.1 and have some hints towards it during the talk, but it is primarily a state-of-the-art discussion. A bit of a subjective selection of personal favorites, topics I find particularly important, and design considerations. This is primarily a design talk, framework design and correspondingly the design of application components running on that framework. So before we get deep into it, just very quickly, my background is co-founding the Spring Framework project back in the days in early 2003, and I've been serving as the Spring Framework project lead ever since. These days, that means everything on github.com/spring-project/spring-framework is my responsibility. So I've also been in charge of evolving Spring Framework to its 5th generation. You'll see some of this shining through in just a moment. This is the fact sheet. So I'm not spending too much time on some of the other things we're doing, but there are a couple of important things being highlighted here. We have a major baseline upgrade. The Spring Framework 5 effort allowed us to finally go Java 8 plus all across the framework codebase. You might not have experienced much of a drawback when using Java 8 before. That's because Spring Framework 4, in particular Spring Framework 4.1, 4.2, 4.3, were strongly Java 8 focused. Lots of Java 8 support for your application components. The framework itself was Java 6 based internally, but had plenty of optional support for Java 8 that it seamlessly activated whenever it was running on Java 8 and whenever it found your code using Java 8 language and API constructs. So you could, of course, use Lambda expressions and method references by convention. You could also use Java util optional, completable future. There are quite a few API types common in Java 8 that you could use in your code, and the framework reflectively adapted to it. So the new part is actually that the framework itself is now Java 8 baselined, and that some of the framework APIs have been enhanced with some overloaded methods that are specifically Java 8 based. So you'll find a few methods that take like Java util function suppliers now as optional callbacks, Java 8 specific API types that we could not expose in our core APIs before. So there is some value shining through to the application, but it is mostly a framework internal upgrade. The other part that we always do is catching up with the latest specifications around us. So Spring Framework 5 comes with dedicated Servlet 4 support, Pinwheel Edition 2 integration, JPA 2.2 support in the specific spots that we need to support them in. For example, a JPA 2.2 stream method, or in Servlet 4, you can inject a push builder in a Spring MVC handler method now. So there is some quite specific support if you choose to run on, say, Tomcat 9 or, well, with JPA 2.2, Hibernate 5.3 is not actually final yet. But if you choose to run on them, then Spring automatically adapts. Otherwise, of course, you can run on any Servlet 3.1 container, JPA 2.1 persistence provider. That is the common baseline now, the Java E7 level. There's also JUnit 5 support, a topic in its own right that is sometimes presented at conferences in combination with Spring 5. Dedicated JUnit 4 integration. We have been sponsors of the JUnit 5 open source effort and have been the first framework shipping JUnit 5 integration. And keep updating it actually to JUnit 5.1 and possibly even JUnit 5.2 for Spring Framework 5.1. And of course, there's the JDK 9 topic. Not a core focus of today, just a few words on it. Spring Framework 5 is Java 8 baseline, but it in particular takes the opportunity to support JDK 9 when actually found at compilation or at runtime. So we actually released a week after JDK 9 GA, very intentionally here. If you choose to run a Spring Framework-based application on a Java 9-based deployment arrangement, then the framework naturally understands what you're doing, and it is internally adapting to all the JDK 9 conventions. We don't use API that is deprecated on Java 9. There is actually quite a bit of it. So it's in all its internals, it's already set up for Java 9 compliance on the class path and on the module path, primarily on the class path. We actually quite strongly recommend staying on the class path for the time being. Not so much for Spring purposes, primarily for all the other libraries that you're integrating with. So that's a dedicated topic that we're covering in some talks, and it's in its own right the upgrade path for existing Spring Framework applications in the new JDK release cadence. So for the time being, let's assume we're on JDK 8 or 9 or 10 or to be 11 on your choice, 8 as a baseline. And for the specific topics I'd like to cover today, let's start with component style. There is a state of the art, of course. This is basically, as you know it, Spring Framework 4 style components. Actually, Spring Framework 4.3 style even. The commented out auto-wired annotation on this single constructor here is actually a 4.3 feature. If there's a single non-default constructor that looks like it's designed for dependency injection, then we're using it instead of failing, even when there's no auto-wired annotation on it. But otherwise, auto-wiring annotation is a fine example for dependency injection. The transactional annotation tapping into services, right, like declarative transactions here. Very common, very established. The stereotype annotation on top. All of these features, even fine-tuning registration characteristics through annotations, like the lazy annotation, a lazy init singleton, right? Hinted at through an annotation that sits on the class. This is part of a very specific component model, the annotation-based component model, that we've took to quite some level in Spring Framework 4. And in many ways, Spring Framework 4.3 is kind of a sort of conclusion of the annotation-based efforts. So almost everything we technically can do is already in Spring Framework 4.3. This keeps being state-of-the-art in Spring Framework 5, even if many of those features have been introduced in 4.2 or 4.3. Composable annotations, ever since 4.2 supported all the way throughout the framework, building your own annotations, custom annotation types, putting them on your classes and reusing those custom annotations that you built, combining certain characteristics through meta annotations, is a very powerful design feature. Not as commonly used as other features in Spring, of course, but if you find yourself repeating certain characteristics in several components of yours, by all means, try to combine them into a custom annotation. Building a custom annotation, including it in your code base, is nothing unusual. And we've taken this to quite some level in Spring Framework 4.2 and 4.3 in particular. Spring Framework 5 is actually significantly faster than before, it should be at least. Configuration classes. The configuration class approach has been introduced in Spring Framework 3, taken to its current level in Spring Framework 4. Nothing unusual either, but we're seeing a different version of expressing yourself here in just a moment. Keep in mind that configuration classes are essentially nothing but a managed component instance with a couple of factory methods. It's annotation-declared factory methods with return type inferred component type hints, like here. So also an annotation-based model for having factory methods creating new instances for the container. More importantly, the container deriving a bean definition from them. So it's actually sort of implicit. The container scans all the configuration classes, looks for @bean annotated methods, and internally registers a so-called bean definition pointing to that factory method for every single one of them. Part of the annotation-based component model, of course. And last but not least, in this component model, we have the endpoints. Spring MVC, regular controllers as a fine example, but it's not the only one. If you look at the Spring messaging module, Stomp on WebSocket support, for example, or Spring integration, JMS endpoints, they all follow the same design. Regular Spring managed components, they are all receiving the same management. A stereotype on top that says here, in this case, REST controller, inferring some default characteristics from it, and annotated handler methods. Every single one of those methods is being detected by the container again, in this case by the dispatcher servlet. It scans @controller classes for those endpoint methods, registers, in this case an HTTP endpoint, for every one of those methods, inferring the mapping information from an annotation and dispatching to this handler method for processing the actual request. There's a couple of nice features introduced here in this model over the years, like the method parameter annotations. So instead of just saying long ID and hoping that the container knows what to do with it, it's usually a good idea to be explicit, say this ID is meant to be resolved from a path variable, which is a parameter level annotation, referring to the parameter above here. Well, you've probably seen most of this. The component model in Spring Framework 4 remains a first-class story on Spring Framework 5. It is the mainstream usage model, by any means. Keeps being the mainstream model. So we continue this very well-established and very comprehensive annotation-based story with all of its benefits and all of its trade-offs. Usually with detecting those loosely coupled components in the class path. Alternatively, you may also register all of those endpoints programmatically already, so there's already quite a bit of stuff that you can do differently with annotation-based components. But in Spring Framework 5, we set out on a different mission, challenging ourselves, challenging the framework, by trying to take a quite radical different perspective. What about registering Spring-managed beans and Spring-managed endpoints in a programmatic fashion, in a purely programmatic fashion? What about not using any annotations, not using component scanning, at least not usually, and avoiding reflection, potentially not using any reflection in the entire setup? What would that mean, right? And in Spring Framework 5, we introduced a couple of dedicated features going into this very direction. This is a rather extreme perspective. Keep in mind that the real world usually is somewhere in between. Spring has always been about supporting all the shades of gray, in combining many of the features as you see fit, as it makes sense in your architecture, in your domain. So these are, of course, features that can be used in this pure fashion, no reflection, no annotations. But it can also be combined, of course, with annotation-based features, just allowing you to programmatically register factory methods, sort of, and express other characteristics through annotations as you always did. Your choice, your call. There's a little bit of, there's some nice things that go with this that we had to do for that to be possible. Even if it looks very simple and straightforward in the end, there's actually quite a bit of support underneath the covers, like the nullability topic, that we'll return to a little bit later. Most importantly, we have not only set out for a functional style, as in Java 8 functional, right? As in Lambda expressions, as in method references, as in the Java util function package or the Java util stream type, Java util optional, this sort of model that Java 8 introduced. This is our primary inspiration for sure, but it has not been the only one. The other part was Kotlin. The other major driver was Kotlin. Kotlin has a couple of distinct qualities that make it a perfect candidate for functionally oriented programmatic purposes. And of course, it can also be used for implementing annotation-based components, but it is particularly suitable for a functional API style. And in Spring Framework 5, we don't just let the obvious happen, like you choose to use Kotlin and things just work, you call a Java API. You could do that before if you wanted to. In Spring Framework 5, we go a significant step further. We ship plenty of Kotlin extensions all across the framework. So the standard Spring Framework jars that you get from Maven Central, like Spring Context jar, Spring Webflux jar, those jars actually contain Kotlin support code, optional extensions for well-established Spring Framework types. For example, generic application context, a very central class in the core container, has a generic application context extensions.kt file. In Spring Context, whenever you choose to use Kotlin, the Kotlin compiler, by convention, naturally finds those extension types. So from a Kotlin perspective, you don't just see the Java type, you see the Java type and a few Kotlin extensions on it, which is really nice. We were able to do something along those lines with Groovy before. Java 8 default methods go into that direction. But the Kotlin extensions really allow us to take this to a very serious level where the experience of using Spring Framework 5 APIs with Kotlin is very idiomatic. A couple of overloaded methods mostly, but they really improve the usage experience through dedicated support for Kotlin K-classes and for Kotlin functions. So much for a little bit of background. A couple of examples for you. This is what, in essence, functional registration looks like using the Java 8 language. So the aforementioned generic application context always had methods like register bean definition, metadata-oriented methods. It now has a couple of overloaded register bean methods that are specifically designed for functional registration purposes. And illustrating a few points that are particularly important here. This one is sort of simple, right? It just says, what about registering a type foo and doing default conventions for everything else? Right. That's like registering a standard component with just a stereotype on it, but it can be done programmatically. It gets interesting below, right? The bar class is registered with what we call an instance supplier. So we register a component of type bar, receiving a bean definition for the core container. And whenever the container needs to create a new instance of bar, it will dispatch not to an annotation-based factory method, not to a default constructor either. It will actually call this little lambda expression, which technically is a Java util function supplier. We call them instance suppliers. So for a singleton, it's the container's choice when to trigger this, usually only once, right? For a lazy singleton, that might be on first use. For a scoped bean or a prototype, this may actually be invoked quite often. In the version below, we essentially do the same thing, but there are two noteworthy differences. Instead of just registering bar with an instance supplier, we enrich the metadata behind it with a lazy init flag. So instead of saying @lazy on the component type, we provide one more lambda expression in line in the same call, right? We call them bean definition customizers. It essentially receives the bean definition right before it's registered with the container. So you can do anything you're able to do on the good old, actually 15-year-old bean definition model. The bean definitions can, for example, they can be enriched with lazy init flags. They can have qualifiers added. You may modify them you may add attributes that post-processors detect. You may do anything you want and anything you were always able to do when you're programmatically building bean definition metadata. It usually works like this. There can be any number of customizers. So if you want to set two things on a bean definition, the easiest way to do it is just one more line here. Just any number of bean definition customizers, it's a var arg underneath. So you don't even have to resort to a lambda code block for doing more than one thing. Now, another noteworthy difference while we're at it, what about this one, right? Foo new. Well, this is essentially expressing the same thing as above, calling the default constructor of foo. The main difference is that we're explicitly specifying an instance supplier instead of relying on default instantiation. Simply speaking, this one calls class new instance, which technically is reflection. This one dispatches to an instance supplier that is bound through a Java 8 method reference to the default constructor on the foo class. This one is a straightforward invoke dynamic instruction in the bytecode to the constructor, no reflection involved. So if you wanted to take it to a sort of extreme level, then always being explicit about instance creation is what we recommend on here. If you'd like to refer to other beans, and if you already sense this from here, right, then you just call back to the container, asking it to give you an instance to retrieve like an instance of foo for you that you're passing, in this case, into the bar constructor. So instead of detection of auto-wired fields methods or a selection of constructors based on the auto-wired annotation, you're very explicit here. You're simply calling back to the container. This is one area that we are going to improve on in Spring Framework 5.1 through a couple of feature ideas we have for more flexible and more sophisticated retrieval APIs. Like this idea of a bean stream that you can configure with a couple of selectors, and that ends up in a pre-selected set of beans, or even a single bean if you request so, in a nice little chained sequence of calls. But for simple purposes, I just want the primary instance of foo, simply do context get bean foo. So this is the Java 8 version, right? Now, what does this look like with the Kotlin extensions? The Kotlin extensions on generic application context are, as mentioned, they are picked up automatically by the Kotlin compiler. So just do this in a KT file and compile it, and you will be able to express yourselves a little bit differently. Like in what I'm calling Java style above here. This looks still very close to the Java example, right? You're essentially saying register bean foo class here, and the bar variant is interesting because it's a little more concise. Instead of saying bar.class, and here's an instance supply of 4 bar instances, you're saying just a Kotlin function that builds bar instances and calls back to the container. The easiest way to do this in a pure function here is actually to call it, because the function receives the application context as kind of an incoming argument. You could also call back to the outer context instance if you chose to do so. But the main difference is you don't repeat the bar part. You're not saying bar.class anywhere. Bar is inferred from the instance supplier. We can do that in Kotlin because the Kotlin compiler understands Kotlin functions and compiles them into a runtime representation of the Kotlin function that allows us to reliably infer the return type. In other words, if you specify an instance supplier that returns bar, the framework can find out about this at runtime and knows that you're registering an instance of bar. Whereas with a Java 8 function, a Java 8 lambda expression or a Java 8 method reference, this is not quite possible. A Java 8 method reference or a generified Java 8 lambda expression is basically this weird little thing that returns something to us. So you have to be explicit upfront so that we know upfront what kind of bean class you're instantiating here. All right, so Kotlin, just by the very nature of its function support in the Kotlin compiler, allows us to have a more concise representation. The version below here is even more radical, I would argue. This is what I'm dubbing the Gradle style usage. These are just my terms for it. The above because it looks like Java code in many ways. The below because the Gradle DSL. If you're using the Gradle build tool and you're using the Kotlin DSL for Gradle, looks quite like this. So stylistically, this is just a variant of the Kotlin language calling the same APIs, where you are generically declaring what you're registering, since the Kotlin compiler retains generics at runtime in a special representation that we can use through Kotlin reflection at runtime. This is, for us, completely inferable and actually sufficient for doing our job. And even a little bit more concise. Personally, I find it a little more unusual as well, so I intend to go with the Java style. All right, so much for functional bean registration and the component style discussion. Now, let's go on to reactive architectures. I'll keep this rather brief because there has been a dedicated talk about it before, but I'd like to highlight a few very important points before we go into the bonus section with a couple of little hidden things, hidden gems that we also have and don't often talk about. All right, so for reactive purposes, our fundamental model in Spring Framework 5 is a reactive streams embracing, right? We embrace the reactive streams initiative that grew out of the Reactive Manifesto. This is a low-level abstraction for back-pressure-driven interaction between a publisher and a subscriber. It's essentially a way for different components to cooperate at runtime, a sort of fancy stream interaction model for non-blocking stream interaction. Publishers basically know how to produce data when a subscriber asks them to actually hand them a few elements. So the subscriber is in charge. Through the subscription, it kind of asks the publisher, whenever the subscriber is ready to process them, it asks the publisher to produce further data to them. Unless a subscriber starts triggering this, the publisher doesn't do anything. The publisher does not just pump data to the subscriber and the subscriber blocks or has a really long buffer filling up. And the subscriber is not blocking either. If the publisher is not ready yet, the subscriber just basically sits somewhere in a processing pipeline and is waiting for a callback. In none of those cases, we ever block a thread. It's a completely non-blocking stream interaction model at a pretty low level. Low level means that, for example, data store drivers would implement this. Reactive web stacks, web engines would implement this. Reactive composition library would implement this. But at the application level, all you would do is use those higher level programming models, and you rely on reactive streams interaction to happen underneath the covers for you. The way we did this is also worth elaborating on, because in Spring Framework 5, you essentially have two very fundamental choices for server-side web stacks. You can choose to be on a servlet-based stack with everything that it brings with it, right? Typically using blocking I/O, running on any servlet container, say Tomcat, Jetty, Undertow, with Spring MVC, the well-established Spring MVC programming model on top. The servlet API actually shines through. It's the central abstraction, right? So in a Spring MVC handler method, you may declare an argument of type HTTP servlet request, or HTTP servlet response, or HTTP session. You may choose to have very direct access to servlet facilities, but more importantly, all the abstractions are based on the servlet interaction model. And in the servlet world, when an HTTP request comes in, there's this large servlet container thread pool. You receive one of those threads. In the Spring MVC case, we dispatch to your handler method, to your get mapping method, within such a thread. And for the entire execution of the handler method, until you're basically done producing the response, you're always in that same request thread. And then it goes back to the servlet container pool at the end. This is a well-established model, but it's actually a very specific model, a very specific, almost a little bit artificial abstraction, because underneath the covers, networking stacks actually work differently. They are kind of async by nature. So we kind of have this thread-bound imperative model on top of an actually asynchronous networking stack underneath the covers. Works pretty well, but it has its limitations. What if the servlet container thread pool is exhausted, right? All the threads are busy waiting on something. If there's no thread left, you can't even process an index HTML request anymore against, at least against that particular server. So you may in particular run into limitations in challenging scenarios, high load scenarios, scenarios with very uneven load, with sudden spikes of load. So it has its limits in particular under more demanding conditions. In parallel to that, because that keeps existing in Spring Framework 5. If you have an existing Spring MVC application, just upgrade it to Spring Framework 5 by changing your Maven pumps, and you can keep running on the Spring MVC stack as you know it, with all the integrations that you may choose to use. All the integration APIs are basically still in action. There's a little bit of reworking in many areas of Spring MVC in 5, but nothing that would really break an application. In parallel to that, we introduce a new web architecture, a new web stack in Spring Framework 5. So there's Spring Web MVC, the module, on the left. And the right is basically Spring-WebFlux, the new module. In Spring WebFlux, we have a non-blocking interaction model, reactive streams-based, with Project Reactor as our central kernel managing the reactive streams interaction for us. It may run on the most sophisticated networking stack out there in the JVM landscape on NetI. That was one of its primary design goals, that we're able to run on NetI. You can also run on a sophisticated enough servlet container with proper support for Servlet 3.1 async I/O streams. It's a bit of a niche feature in servlets, but there is something that we can adapt reactive streams to. It's a different mode of operation. So you may choose to use Tomcat or Jetty or Undertow in particular. We have dedicated support for those three. But they are kind of used in a different mode, not as servlet containers, but as reactive HTTP engines. In particular, in Tomcat and Jetty, a lot of work has gone into them, improving their usability as reactive HTTP kernels. So their names may sound familiar, but they are not actually servlet containers. The servlet container does not, the servlet API does not shine through here. The abstraction is our common web abstraction based on reactive streams. It's not the servlet API. There's no servlet container thread pool. There's an event loop underneath those covers. And the event loop is usually set up for just the number of threads that your hardware actually has, right? Basically, the number of available processors, the number of CPU cores. Very small setup, strong cache locality at the CPU level, and a non-blocking interaction model on top. So those threads are just serving whoever is actually ready to be served. But none of those operations is allowed to block, because you would block one of the threads in the event loop, which is a big no-no. Now, it gets a little more shaded in colors, right? The shades of gray I mentioned before. Spring MVC and Spring Web Flux actually share quite a bit of stuff. They share common Web Foundation support. They share an annotated ad controller model that is very similar as it can be in design and style between those two worlds. They share the ability to have some reactive support. For example, you can choose to use the reactive web client that we have in Spring Framework 5 in a Spring MVC setup. There's even a little bit of reactive support in a servlet container setup that we support. Fundamentally, you're making a decision between two worlds. Servlet container model on one end, or an event loop-based reactive web flux stack on the other end. There are shades of gray in between in choosing the servlet container stack and doing a little bit of reactive interaction with it. It's not as efficient as an event loop setup would be. There's also the ability to use like Tomcat, Jetty, or Undertow as servlet containers or as reactive HTTP engines, as we discussed. But then there's a few things that clearly separate the two. You've got imperative logic, right? You're making assumptions about owning the thread. You're using thread locals. You're using thread local-based features like Spring's add transactional for longer running code, longer than just a few database operations, just a few exceptionary short interactions. You shouldn't be doing this in the reactive world, right? Because those features and those interaction models make assumptions about owning the thread. Maybe the best example, you're using JDBC, you're using JPA, you're using any other blocking data store API, you're probably better off on the servlet stack with Spring MVC, simply because those operations block, and you can't do anything about it because those APIs are designed as purely blocking APIs. The moment that you have some endpoints, some web endpoints that need to block, you're better off on the servlet stack. And doing a little bit of reactive interaction, maybe in reactive endpoints, like for the reactive web client, you may do that on the servlet stack as well, but an event loop is not for you. You can turn that around, though. If you are able to use NetI, or your choice of other reactive web engine underneath the covers, if you have a reactive data store driver, if the data store that this particular service of yours interacts with is reactive, choose Spring Web Flux in its event loop server model. Choose it in order to expose the power of this underlying data store to the web endpoints. So it's from that perspective, it's very bottom-up data store driven. Which kind of data store are you interacting with kind of suggests with web architecture you should be using. Keep in mind, in a microservice architecture, some services might talk to blocking data stores, blocking data store APIs. others, more specifically purposed microservices in such an architecture, may be able to make assumptions about the data store that they're interacting with. There's nothing wrong with mixing those styles in a larger system setup, depending on what the particular service needs to do and the challenges it has to face at runtime. All right, back to the programming model perspective quickly. This is the annotation-based version of a reactive controller. More specifically, this is a Spring MVC annotated controller with reactive endpoint methods. It suspiciously looks like a Spring MVC controller because fundamentally it's the same model, the same annotations, controller on top, get mapping. Even the parameter level extraction of metadata works here, right? Same model. The main difference is the purpose of those handler methods. You might have seen that in the demo session before, might have inferred that from there. If you have a reactive repository, you'll basically have some repository API, some data store API, lower level, that you're calling that returns reactive types, like reactive streams publishers, or RxJava flowables, or reactor fluxes. Exposing those reactive streams publishers from the data store level up to the web layer is exactly what we're doing here. We assume that we have a repository, maybe a Spring Data repository, that is based on the reactive flux and monotypes. Just means return them directly. If there are some extra transformations to add, just add them here. Some extra transformations for the web representation of those entities. Just do it here, if there are some adaptations to make. So the purpose of those handler methods is actually to build a reactive streams publisher for the incoming request. The request has come in. We basically need to process it, and the runtime system asks you for a reactive streams publisher. So the handler method essentially builds just a pipeline of interactions, a pipeline of steps of how to arrive at the outcome for this request, how to produce the demanded response for this incoming request. It doesn't actually process the request yet. The reactive streams publisher goes back to the runtime system. Whenever the data is ready to be processed, the request is fully read, the response is ready to be written, or at least has a large enough buffer ready, then and only then, we start subscribing to your publisher that you gave us and start pumping the data to the HTTP response. So your handler methods need to be non-blocking, basically just build the instructions for how to arrive at the response. Now, for those not having seen it before, what about Mono and Flux here? Well, both of them are perfect candidates here because both of them implement the Reactive Streams Publisher interface. Anything that can be adapted to a Reactive Streams Publisher can be used here. So either a publisher directly. In the Reactor case, you would usually use those composition APIs. Mono for a single element or none, and Flux for a sequence of elements. So it's a little bit like Java util optional and Java util stream, or RxJava single and RxJava flowable. If you happen to call an API that returns RxJava types to you, no problem. Spring Webflux, sorry, understands, Spring MVC as well actually, understands RxJava types. So you could also return a flowable or even an observable from RxJava 1 directly here. The runtime system knows how to adapt them and to make them a part of a reactive streams pipeline. But in this case, we usually receive the reactor handles, Flux and Mono. There are no more, just those two, one or none, and a stream of elements. So the functional endpoints, just for an example of what this style feels like, as briefly as possible here. The above shows a router function expressing the same web interaction that we've seen here in a different programmatic model. So we're with a couple of static imports in place. We can express ourselves like route. Here's the incoming predicate, the kind of request that comes in here. Delegate to that handler method. And for this other route, get users / users, delegate to the other handler function. Router functions and handler functions, the programmatic representation for what Spring MVC style controllers usually do for you. So the incoming request is routed to one of those methods, and those methods receive an incoming server request, and you need to return essentially a reactive streams publisher for the outgoing response. And there are convenient ways of doing this, but they are slightly different, right? Like in this case, where we need to extract a path variable, there is no flexible signature, no at path variable annotation. You're asking the request to extract a path variable, you're converting it to a long, and you're passing the result to the repository find by ID method. And then you're done. Well, almost, because this is a publisher for the body, and the signature actually asks you for the response with its headers. So you need to say status OK, here's the body. And because we're on Java, you need to explicitly say that this is user.class because we can't infer this at runtime for you. If you're using the Kotlin version of this DSL, which we're not looking at today, not in this session, then no user.class because we know we can infer this from the Kotlin function. This is kind of the direct exposure, right? Handler functions adapted to methods, and the methods need to comply to the signature of that interface. Server request going in, server response going out. It looks a little less alien and more concise when you look at it with inline Lambda expressions. The exact same code. Router function, route coming in, the request matches. We dispatch to this inline Lambda expression, just say like, here's how to arrive at a response. Do this for me, please. And you return from the inline function. You're never seeing the server request signature or the monoserver response return type. All right. And the aforementioned reactive web client, as you would expect, follows the same design. So it's a very natural part of this setup. What about, for example, just receiving a mono or receiving a flux straight from a web client API for direct exposure, direct returning to your web endpoint in a microservice architecture where you're calling some other microservice programmatically? This is the way to do it. Comes out of the box with the Spring Web Planks module in Spring Framework 5. All right. I'll use the remaining few minutes to give you a few hints about what else we did. I've mentioned nullability. The entire Spring Framework codebase, in particular the API level, has add-nullable annotations now. Non-null by default, nullable where it's actually nullable, for incoming parameters and for outgoing return values. This is surprisingly useful. The Kotlin compiler naturally understands this and allows you to assign, like the outcome from a Spring API call, to a non-null variable declaration, if it's explicitly marked as nullable, or as not nullable. It makes assumptions about nullability against target APIs based on nullable annotations. In Java, it's just for us a verification that the code is doing what it's supposed to do and making the right assumptions about nullability. So we use IntelliJ IDEA's introspection features to tell us that all our nullable and non-null declarations in the codebase actually make sense. And nullable is exposed in the Java doc, is exposed in the API that you're interacting with. Even if you are calling Spring API, look at its nullability declaration, and you may make safe and reliable assumptions against those, right? If a Spring API is not marked as nullable, you're never going to receive null from it. So it also has value in Java, but it has particular value in Kotlin, where otherwise you would not be able to assign such an outcome to a non-null declaration to begin with. We have a few new nice little methods in the dependency injection space. And at AutoWide, if you have object provider for a bean, where you can dynamically ask for instances, there are a couple of nice new methods. First of all, there are examples for nullability, right? Like here. What about get if available, get if unique? If it's not available, if it's not unique, then you get null, right? And it's explicitly marked as nullable now, so that you know. But there are nice other methods using Java util function suppliers and consumers. Give me an instance of that bean if available. Otherwise, this supplier here, an inline Lambda expression usually that you specify, produces a default instance, returns a default instance that you should return to me instead. Or do it in a more functional style. If available, here's a consumer that knows what to do with it. Otherwise, just skip it. So there are some new methods, a little functionally oriented, nicely connected to the nullability story, in APIs that are primarily used within the annotation-based model. We have direct support for data class binding now. Data classes are a broad topic on its own. Just think about Kotlin data classes. Think about Lombok data classes, the Kotlin data class, Lombok data classes. Basically, the constructor receives all the data. The object itself is immutable and has usually default equals hashcode toString implementations. We understand that pattern now in standard data binding scenarios, both in Spring MVC and in other places, where if you present such an object to us as a binding target, then we know that we shouldn't look for setter methods. We know that we use the primary constructor of those classes to pass all the data in, inferring the names from the signatures, from the constructor parameter names, and calling this automatically without any special setup, just naturally detecting it. Makes a lot of sense for Kotlin, makes quite a bit of sense for Lombok, and even for standard Java classes following the same convention, single constructor, final fields, manual equals hashcode toString. Even if you follow those conventions in standard Java code, this data class binding model is a really nice feature. All right, so we're almost at the end. Just a few hints to wrap up. We have dedicated completable future support in our scheduling abstractions now. You can nicely adapt them. You can use Java time, instant, and duration for specifying scheduling tasks programmatically. You might see a theme here, and it's all the improving of the programmatic APIs for Java 8 exposure and for a more functional style. So we also touched quite a bit of the task execution and scheduling abstractions for programmatic async processing outside of the reactive space, using standard Java completable futures. So there's no reactiveness in here, but we nevertheless upgraded them for better usability on Java 8+ and better monitorability, actually. We upgraded our resource API and SPI. It's NIO2-based now, which we can reliably assume on Java 8. We have a build-time components indexer, which is also a really nice feature, sort of a little bit of a niche in terms of when you really need it. But if you've ever found a lot of time spent on class path scanning, consider adding the components indexer to your build script. It will create a little index file for your jar files, and we look at those index files to short-circuit the class path scan. So if there's all the information in there in that index file, we don't need to scan your class path on startup. We are using the information that your build script put into those index files. A really nice model. If you'd like to look it up, look for components indexer in the reference documentation. Last but not least, we have a new logging arrangement. If you've ever found yourself excluding some logging API, like the standard comments logging API, and including the SLF4J over JCL bridge, if you've ever found yourself doing this, don't worry no more, right? In Spring Framework 5, it's all streamlined. There's a custom logging bridge with direct support for both SLF4J and in particular for log4j2. No manual excludes, no manual includes, no bridges. Just dump SLF4J or log4j onto the class path, and logging is finally going to work out of the box as expected without any custom setup in your pumps. All right, so much really for this little tour. So thanks for your attention so far. Just a quick summary of things we're doing. Spring Framework 5, mostly about programmatic usage in terms of the new APIs there, a functional style, reactive web architectures. We're continuing this in 5.1. I've already mentioned a few things like the beanstream idea. JDK 11 support is a key topic in 5.1. If you look at the target date, that's no coincidence. JDK 11 as the next long-term support release out there is something we strongly care about, giving you a choice of JDK 8 and JDK 11 as long-term support branches as of 5.1, and there are a few things we need to do for you to have a warning-free experience on JDK 11, both on the class path and on the module path. And there's a little bit of extra value even. JDK 11 has a new HTTP client API, finally in stable form, that we consider using in a few places. So there might be some nice bonus features connecting to our web stories as well. All right, so much for this tour. Thanks for the extra attention. I went a little bit over time. Enjoy the rest of the show. And there's a spring BOF tonight. For any discussions, please join us for the BOF at like 7:30. Thank you. And if there are any questions right now, please just come up to the stage. We can take it from here. Thanks.